What is solenoid? How does it function and its application? A solenoid is a type of electromagnetic device that converts electrical energy into mechanical motion. It consists of a coil of wire, usually wound in a cylindrical shape, that produces a magnetic field when an electric current passes through it. This magnetic field exerts a force on a movable metal core, often called a plunger or armature, causing it to move in a linear fashion. The solenoid's ability to control this motion precisely is what makes it widely used in various applications. A solenoid works by using the principles of electromagnetism to convert electrical energy into mechanical motion. Below is a step-by-step explanation of how a solenoid operates. 1. Electrical current through the coil. When an electric current is passed through the solenoid's wire coil, it generates a magnetic field. This coil is usually wound in a cylindrical or helical shape, often around a hollow or solid core. 2. Creation of a magnetic field. The current flowing through the coil produces a magnetic field inside and around the coil. This magnetic field resembles the field produced by a bar magnet, with a north and south pole, but concentrated along the axis of the coil. The strength of this magnetic field is proportional to the amount of current flowing through the coil and the number of turns in the wire. 3. Magnetic field acts on the core. Most solenoids have a ferromagnetic core, typically made of iron or steel, that is placed inside or near the coil. This core can move freely along the axis of the coil. The magnetic field generated by the current pulls this core toward the center of the coil, where the magnetic field is strongest. If the solenoid is designed for linear motion, the core moves in a straight line. If the solenoid is designed for rotational motion, the core rotates instead. 4. Mechanical motion. As the core moves, this movement can be harnessed to perform mechanical work. For example, linear solenoids. The core moves in or out, pushing or pulling on mechanical parts. Rotary solenoids. The core's motion is converted into rotational motion. This movement can be used to push levers, open valves, move gears, or perform other mechanical tasks. 5. Return mechanism. Optional. When the electric current is turned off, the magnetic field disappears, and the core is no longer pulled toward the center. To return the core to its original position, solenoids often use a spring. The spring pushes or pulls the core back into place when the magnetic force is no longer active. In some cases, gravity or another external force may be used instead of a spring. 6. Repeated activation. By controlling the electric current, the solenoid can be activated repeatedly. When the current flows, the solenoid moves the core, and when the current stops, the core returns to its rest position. This on-off cycle can be used in many applications that require precise mechanical actions. Key points of operation. Electromagnetism. The core moves due to the magnetic field created by the current in the coil. Force control. The force exerted on the core depends on the current, number of turns in the coil, and the material of the core. Mechanical output. This force is used to move mechanical components, like opening a valve or moving a latch. Summary of the solenoid's operation. Electricity is applied to the coil. Magnetic field is generated within and around the coil. Core, plunger, is attracted to the center of the coil by the magnetic field. Mechanical motion is created, which can be harnessed for tasks like switching, moving, or activating mechanical parts. When the current is stopped, the core returns to its original position, usually with the help of a spring. This on-demand movement, controlled by electrical signals, makes solenoids extremely versatile and useful in various mechanical and electronic systems. The key components of a solenoid are critical to its function as an electromechanical device. Each component plays a role in converting electrical energy into mechanical motion. Here's a breakdown of the essential parts. 1. Coil, wire winding. Material. Typically made of copper or another conductive material, the wire is wound tightly in a helical or cylindrical shape. Function. When electric current flows through the coil, it generates a magnetic field. The strength of the magnetic field depends on factors like the amount of current and the number of turns in the wire. The coil is the heart of the solenoid's electromagnetic function. 2. Core, plunger or armature. Material. Usually made of a ferromagnetic material like iron or steel. Function. The core is a movable metal rod or cylinder inside or adjacent to the coil. When the magnetic field is activated, it pulls the core into the center of the coil. This linear motion is what creates the mechanical output of the solenoid. The core can either push or pull mechanical parts depending on the design of the solenoid. 3. Frame or housing. Material, often made of metal or plastic. Function. The frame provides physical support and protection for the internal components of the solenoid. It may also help to concentrate the magnetic field and prevent interference with external components. In some designs, the frame also helps guide the movement of the core, ensuring smooth motion. 4. Spring, optional. Material, usually made of steel or other flexible metals. Function. The spring is used to return the core, plunger, to its original rest position when the electric current is turned off and the magnetic field disappears. Without the spring, the core might stay in the pulled-in position. Some solenoids use external forces like gravity instead of a spring. 5. Pull pieces. Material, ferromagnetic materials like iron. Function. These are stationary components within the solenoid that help to enhance and focus the magnetic field. They direct the magnetic force towards the core, making the solenoid more efficient by improving the magnetic flux path. 6. Bobbin, coil former. Material, typically made of plastic or non-conductive materials. Function. The bobbin is the structure around which the wire coil is wound. It holds the wire in place and provides insulation between the coil and the core or frame. The bobbin also helps maintain the coil shape and protects the winding from damage. 7. Yoke, magnetic field concentrator. Material, made of ferromagnetic material. Function. The yoke helps direct and concentrate the magnetic field produced by the coil, improving the efficiency of the solenoid. It minimizes the leakage of the magnetic field and enhances the force applied to the core. 8. Electrical terminals, contacts. Material, usually made of conductive metals like copper or brass. Function. These are the points where the solenoid is connected to an electrical power source. The terminals provide the electrical connection that allows current to flow through the coil. Summary of key components and their functions. Coil generates the magnetic field. Core, plunger, moves in response to the magnetic field, producing mechanical motion. Frame houses and supports the components, sometimes focusing the magnetic field. Spring returns the core to its rest position when current is off. Pull pieces direct the magnetic field for efficiency. Bobbin holds the coil windings in place and insulates components. Yoke enhances magnetic efficiency by concentrating the magnetic field. Terminals provide the connection to the power supply for the coil. Together, these components allow a solenoid to function effectively as an actuator, converting electrical energy into a controlled mechanical movement. There are several types of solenoids, each designed for specific applications and mechanical functions. The classification is typically based on the kind of motion the solenoid produces, the way it operates, and the level of precision required. Here's a breakdown of the main types of solenoids. 1. Linear solenoids. Description. These solenoids produce linear, straight line motion when activated. Operation. When the coil is energized, the core or plunger moves in a straight line, either pulling or pushing depending on the design. Applications. Widely used in applications that require direct mechanical action, such as electromechanical locks, automotive door locks, vending machines, valve actuators. Types of linear solenoids. Push solenoid. The core moves outward from the coil when energized. Pull solenoid. The core is pulled inward when the coil is activated. 2. Rotary solenoids. Description. These solenoids produce rotational or angular movement rather than linear motion. Operation. When the coil is energized, the core moves rotationally, typically between 25 degrees and 90 degrees, depending on the design. This motion can be used to rotate gears, levers, or other mechanical parts. Applications. Common in devices that require limited angle rotational motion, such as automated switches, camera shutters, circuit breakers, medical devices. 3. Holding solenoids. Description. These solenoids are designed to hold or maintain a specific position or load when energized. Operation. Unlike other solenoids, which are designed for quick movements, Holding solenoids use the magnetic field to keep the core in place for extended periods. Applications. Used where long-term activation is needed without continuous motion, such as magnetic clamps or holders. Security systems. Electromagnetic brakes. 4. Proportional solenoids. Description. These solenoids provide variable force or displacement in proportion to the input current. Operation. The force exerted by the solenoid is proportional to the amount of current flowing through the coil. This allows for fine control of the position and force of the core. Applications. Used in systems requiring precise control of force or position, such as hydraulic and pneumatic valve controls, fuel injectors and engines, medical dosing equipment. 5. Latching solenoids. Description. These solenoids are designed to maintain their position even after the power is turned off. Operation. Latching solenoids use a permanent magnet or mechanical latching mechanism to hold the core in position without continuous power. Power is only required to change the state, latch or release. Applications. Ideal for applications where energy conservation is important, such as power-efficient locking mechanisms, energy-saving switches, actuators and battery-operated systems. 6. AC and DC solenoids. Solenoids are often classified based on the type of current used to power them. AC solenoids. Description. Operate using alternating current, AC. Characteristics. These solenoids are often used in high-power applications, but they may suffer from noise or vibration due to the alternating nature of the current. Applications. Used in industrial machinery, large electromagnets, or high-power switches. DC solenoids. Description. Operate using direct current, DC. Characteristics. These solenoids provide smoother and quieter operation, often used in precise, low-power applications. Applications. Found in automotive systems, small devices, and sensitive electronic equipment. 7. Tubular solenoids. Description. Tubular solenoids have a cylindrical housing that encloses the coil and core. They offer a higher magnetic efficiency due to their closed design. Operation. These solenoids typically provide higher force over longer strokes than other solenoids. Applications. Used in applications requiring strong pulling or pushing forces, such as industrial machinery, railway signaling systems, automated locking systems. 8. Open frame solenoids. Description. These solenoids have an open or exposed frame, which allows for easy installation and cooling, but at the cost of reduced magnetic efficiency. Operation. The core moves freely within an exposed frame, and they are often smaller than tubular solenoids. Applications. Suitable for light-duty applications where cost is a priority, such as home appliances, office machines, e.g., printers, coin dispensers. Summary of solenoid types. Linear solenoids produce straight-line motion, used in locks, valves, etc. Rotary solenoids create angular motion, used in switches and camera shutters. Holding solenoids maintain a position under load for long periods, used in clamps and security devices. Proportional solenoids provide variable force, used in precise control systems. Latching solenoids retain position after power is off, used in energy-efficient applications. AC/DC solenoids, classified by the type of current, used in either high-power or low-power systems. Tubular solenoids, enclosed in cylindrical housings for greater efficiency, used in high-force applications. Open-frame solenoids, simple and cost-effective for light-duty tasks. Each type of solenoid serves a distinct purpose, making them versatile components in various mechanical and electronic systems. Solenoids have a wide range of applications due to their ability to convert electrical energy into controlled mechanical motion. Their versatility makes them essential in many industries, including automotive, industrial automation, medical devices, and consumer electronics. Here are some of the common applications of solenoids. 1. Automotive industry. Starter motor. Solenoids are used in car starter motors to engage the pinion gear with the engine's flywheel to start the engine. Fuel injectors. Solenoids control the precise opening and closing of fuel injectors, ensuring efficient fuel delivery in internal combustion engines. Transmission systems. Solenoid valves help control the flow of transmission fluid, enabling automatic gear shifts. Locking systems. Solenoids operate door and trunk locks in modern vehicles, enabling remote locking and unlocking. Anti-lock braking systems, ABS. Solenoids control hydraulic pressure in the braking system to prevent wheel lockup during braking. 2. Industrial automation. Solenoid valves, used in fluid and gas control systems to automatically open or close valves. Applications include HVAC systems, controlling the flow of refrigerants or gases in heating, ventilation, and air conditioning. Water treatment, regulating the flow of water, chemicals, or gases in purification and filtration systems. Pneumatics and hydraulics. Solenoid valves control compressed air and hydraulic fluid flow in machinery, enabling automation of mechanical systems. Actuators. In automated systems, solenoids act as actuators to control levers, gates, and switches. They are used in robotics. Solenoids control gripping mechanisms and movement in robotic arms. Packaging machines, actuating conveyor belts, sealing mechanisms, and cutting tools. 3. Medical devices. MRI machines. Solenoids are used to generate strong magnetic fields in MRI, magnetic resonance imaging, machines, which help in non-invasive medical imaging. Drug delivery systems. Solenoids control the precise dispensing of fluids or medications in automated systems like insulin pumps or 4-drips. Respirators and ventilators. Solenoid valves regulate airflow and oxygen delivery in medical ventilators, ensuring the correct breathing support for patients. 4. Consumer electronics and appliances. Printers and copiers. Solenoids are used in printers to control the movement of paper, ink heads, and trays, ensuring precise operation. Vending machines. Solenoids control the dispensing of products like snacks, beverages, or change by actuating levers that release items. Washing machines. Solenoid valves regulate the flow of water into washing machines, controlling the wash cycle and water levels. Dishwashers. Solenoid valves control the water flow in dishwashers, determining when to fill and drain water. 5. Locks and security systems. Electromechanical locks. Solenoids are widely used in security systems to control locking mechanisms. They are found in door locks, magnetic or mechanical locks that can be activated remotely. Safe locks. Solenoids control locking bolts in safes, allowing for remote unlocking with keypads or biometric sensors. Access control systems. Used in electronic security systems to control the locking and unlocking of doors based on authorized access. 6. Aerospace and defense. Aircraft systems. Solenoids are used in hydraulic systems, fuel control valves, and actuators in aircraft to control movement and regulate fluid systems. Missile and defense systems. Solenoids control the actuation of mechanical systems and defense equipment, including launch mechanisms and control surfaces. Landing gear systems. Solenoids control hydraulic valves that extend and retract landing gear in aircraft. 7. Home appliances. Refrigerators. Solenoids control water dispensers and ice makers in refrigerators by opening and closing valves. Water heaters. Solenoid valves control the flow of gas or electric power to regulate the heating elements in water heaters. Microwaves. Solenoids control the door locking mechanisms and magnetron operation in microwaves. 8. Relays and switches. Electromechanical relays. Solenoids act as switches in electrical circuits, where a small electrical signal can control a larger power circuit. Circuit breakers. In power distribution systems, solenoids are used to automatically break the circuit when a fault is detected, protecting electrical systems from overloads or short circuits. 9. Amusement and gaming machines. Pinball machines. Solenoids control the movement of flippers, bumpers, and ball launching mechanisms in arcade games. Slot machines. Solenoids are used to control the release of coins or tokens and to engage or disengage reels in slot machines. 10. Textile and manufacturing machines. Textile machinery. Solenoids are used in looms and sewing machines to control threading, cutting, and fabric movement. CNC machines. Solenoids control the tool positioning, clamping, and release mechanisms in computer numerical control, CNC, machines used for precision machining. Summary of applications. Automotive, starter motors, fuel injectors, ABS systems. Industrial automation, solenoid valves, actuators, HVAC, water treatment, medical, MRI machines, drug delivery, respirators, consumer appliances, printers, washing machines, vending machines, security, electromechanical locks, safes, access control, aerospace, landing gear, hydraulic systems, defense equipment, home appliances, refrigerators, water heaters, microwaves, electrical circuits, relays, circuit breakers, gaming, pinball machines, slot machines, textile, looms, CNC machines. In summary, solenoids play a critical role in enabling automation and precision control in a vast array of systems across industries, providing reliable mechanical movement triggered by electrical signals. In summary, solenoids are fundamental electromechanical devices that leverage the principles of electromagnetism to perform controlled mechanical movements, making them essential in a variety of industries and technologies.